the Higuchi's model or equation. There are two scientists with the name Higuchi, Takiro, and his brother William. Takiro passed away in 1987, and he is an American chemist who is widely known as the father of physical pharmacy. He invented most of the time-release medications. His brother William is also an American chemist and pharmaceutical scientist, and also is known in his field. He is currently a distinguished professor at the University of Utah. Takiro and William are both distinguished scientists, and each of them published hundreds of publications and models. Some of these models include drug eluted from homogeneous polymer matrix, drug leached from a heterogeneous or granular matrix, soluble drug release from homogeneous solid or semi-solid vehicles, and diffusion of drug from an elastic capsule surrounded by a polymer barrier. Drug eluted from homogeneous polymer matrix. Probably the simplest method of obtaining sustained release of a drug from an oral dosage form is incorporation of a drug in an inert matrix. Inert means insoluble and non-interacting with the biological fluids. Release of the drug from inert matrix occurs by leaching mechanism. Drug particles dispersed in the insoluble polymer matrix dissolve in the penetrating gastrointestinal fluids and are released from the tablet by diffusion. In the original derivation of the model, the drug release was from one direction. This is the drug release. Therefore, the tablet was embedded in wax by coating the lateral and one of the flat sides with molten beeswax. These are the lateral sides, and this is the flat side, and the three sides were embedded in beeswax or molten beeswax, thereby exposing one flat surface of the tablet for the drug release. This is the exposed sides. As the drug is released, distance for diffusion is greater. This is the distance for diffusion will be. The boundary that forms between the drug and the empty matrix recedes into the tablet as the drug is eluted. This is the empty matrix now. This matrix does not contain the drug, while this region contains only the soluble drug, while this region contains the drug that is dispersed insoluble and the drug that is soluble in the matrix system. According to Fick's first law, dm by dt per area S equals dq by dt, and it equals dcs divided by h, where dq by dt is the rate of drug release per unit area of exposed surface of the matrix. Because the boundary between the drug matrix and the drug depleted matrix recedes with time, the thickness of the empty matrix dH through which the drug diffuses also increases with time. Cs is, so H in this case is changing with time. Cs is the solubility or saturation concentration of drug in the matrix. A is the total concentration, dissolved or undissolved, of drug in the matrix, and as the drug passes out of the homogeneous matrix, the boundary of the drug, the dashed vertical line, moves to the left by an infinitesimal distance dh. Okay, as we mentioned before, this is the tablet, okay, embedded in molten wax from three sides, and this is the direction of the release. And also, as we mentioned before, the boundary that forms between the drug and the empty matrix recedes into the tablet as the drug is eluted. This region is totally empty from the drug, while this region contains only the dissolved drug, while this region contains the drug dissolved and undissolved. The infinitesimal amount dq of drug released because of this shift of the front is dq equals a dH minus half cs dH. Consider that the amount released depends on the region of the rectangle minus the area of the triangle. Therefore, a dH reflects the rectangle, and half cs multiplied by dH reflects the area of the triangle. Okay. According also to Fick's first law, dq equals diffusion coefficient multiplied by solubility divided by h and multiplied by the dt. Just rearrangement of the equation, which will be integrated later to obtain the relationship between the boundary between the boundary that forms between the drug and the empty matrix H, and also with the time. After integration of the previous equation and evaluation of the constant C, the following equation is obtained. This is a relationship between the thickness of the empty membrane and time. The equation shows that as the thickness of the empty matrix increases with the increase in the square root of time. The amount of drug depleted per unit area of the matrix Q at time t is obtained by integrating the equation dq equals a dH minus half cs dH. Then if we substitute for h, which is the thickness of the empty matrix, in the previous equation, which is known as the Higuchi's equation, is obtained. According to Higuchi's equation, the amount released per area equals diffusion coefficient multiplied by 2a, where a is the amount, the total concentration dissolved or undissolved of the drug, and cs is the saturation or the solubility, and t is the time. This is known as the relationship between the amount released versus square root of time. The instantaneous release of drug at time t is obtained by differentiating the previous equation. dq by dt equals half diffusion coefficient multiplied by twice a, where a, as we mentioned, is the dissolved or undissolved drug, minus dissolved drug multiplied by the dissolved drug divided by time to the square root. This equation shows that as the time is increased, the release rate is decreasing. So therefore, if we have a drug dispersed in an inert matrix, the release rate will decline with time, and it will not be constant or zero order release. Usually A, which is the total concentration of the drug dissolved and undissolved, is higher or much greater than CS, which is the dissolved drug. Therefore, the equation is being reduced to the following equation, where Q is related to square root of 2a dCS multiplied by time. And the dq by dt is also reduced to the following equation. Based on these equations, we can change the release rate dq by dt by changing or altering either increasing or decreasing the CS, which is the drug solubility of the drug, and also by which can be changed by, for example, changing the interaction with the polymer, for example, by complexation, and also by changing the total concentration. We can dissolve and undissolve. We can also change the rate of the drug release. This is an example on how on the application of Higuchi's model. Example 13.6. What is the amount of drug per unit area released from a tablet matrix at time equals 120 minutes? The total concentration of the drug in the homogeneous matrix A is given, which is 0.02 grams per ml. The drug solubility CS is given, and it is 1 × 10 to the power minus 3 grams per ml. The diffusion coefficient is also given in the question, and it equals 6 × 10 to the power minus 6 centimeters square per second. Q, Higuchi's model, Q equals 2ADCS, all of it to the square root. We have the A is given in the question, D is given in the question, CS is given in the question, and T, the time, is given in the question. The amount released per area equals 1.3 × 10 to the power minus 3 grams per centimeter square. What is the instantaneous rate of drug release? dq by dt equals square root of ADCS divided by 2t, and the release rate at 120 minutes equals 5.5 × 10 to the power minus 6 grams per centimeter square per minute. Release from granular matrices. The difference between homogeneous matrix and granular matrix is that granular matrix contains pores, and the drug is leached through these channels or pores. These are the pores, and the drug is released through these channels or pores. And as you notice, the distance is not a straight line. Therefore, another symbol or parameter or constant need to be defined, which is also tortuosity. So we need to define porosity and tortuosity in heterogeneous systems. Porosity is a measure of empty spaces in a material, and it is the fraction of the volume of voids over the total volume. Porosity between 0 and 1. And tortuosity is a property of curve being twisted. Tortuosity is commonly used to describe the diffusion or the flow in porous media, and it is the ratio between the length of the curve to the distance between its ends. Tortuosity, which is here tau, the symbol tau, and porosity is the symbol epsilon. So in case of granular system, the tortuosity and porosity are taken into account in the Higuchi's model. Therefore, in a heterogeneous system, the amount released per area equals diffusivity or diffusion coefficient multiplied by epsilon and divided by tau multiplied by 2a, which is a drug dissolved and undissolved, minus epsilon, which is a porosity, multiplied by the saturation, multiplied by saturation, multiplied by time, and it's all to the square root. Epsilon is the total porosity of the matrix, and tau is the tortuosity of the capillary system. Epsilon and tau, they are both dimensionless. As we mentioned, porosity is the fraction that exists as pores. Soluble drugs in topical vehicles and matrices. In the original Higuchi's model, zero concentration of the drug at the interface separating the donor and the receiving phase is assumed. This is the Higuchi's model, full drug dispersed in an inert matrix. Rosman and Higuchi proposed a model that applies only to systems where the solubility of the drug is negligible with respect to the concentration in the vehicle. This is also the Higuchi's model for drug dispersed in an inert matrix when A is much higher than CS. Bottari et al. Extended Rosman and Higuchi's model to any homogeneous solid separated from a receptor sink by a planar diffusional barrier. This means that in Bottari's model they do not assume zero concentration of the drug at the interface separating the donor and the receiving phase. This is Bottari's equation, Q square plus 2 dVr AQ minus 2 dVA CST equals 0, where Q is the amount of drug released per unit area, A is the total concentration of the drug in the vehicle or the matrix, CS is the solubility of the drug in the vehicle or the matrix, dV is the diffusion coefficient of the drug in the vehicle, R is the diffusional resistance of the barrier interposed between the vehicle and the receiving phase. When Q square is much higher than 2 dr AQ, the equation reduces to one of Higuchi's model. This is Higuchi's model when A is much higher than the CS. Under these conditions, R, which is a resistance, is no longer significant at the interface between vehicle and receptor phase. When CS is not negligible in relation to A, the vehicle controlled model of Higuchi becomes, this is Higuchi's model, when the A is cannot be considered much higher than the CS. The applicability of Bottari et al. Equation was extended to experimental systems in which A is but a few times greater than the saturation or the solubility. This is the equation, okay, where A, in this case they used A star instead of A, which is the concentration of the dissolved and undissolved amount of the drug, where in this case they use the effective concentration A star, and the effective concentration equals the concentration dissolved or undissolved minus CS, which is the saturation, minus CV divided by 2, where CV represents the concentration of the drug in the vehicle at the interface with the barrier. CV was assumed to be 0 in Higuchi's model. The above equation, okay, can be written as a quadratic equation, and the solution of the quadratic equation is shown below. This is the solution of the quadratic equation, and also this is the simplification of the above equation. If there is a lag time, T is replaced by T minus the lag time for the steady state period. This is the equation when the lag time is added. The value of CV can be determined experimentally once diffusional resistance is experimentally determined, where the CV equals the resistance multiplied by dQ by dt. And the resistance is usually determined by preparing a membrane, this membrane from the same material of the matrix, and the resistance through the membrane is being measured experimentally. This is an example how the Bottari's model is applied to the experimental results. Calculate Q, the amount in milligrams of micronized benzocaine released per centimeter square of surface area from an aqueous gel after 2.5 hours. Assume that the total concentration A equals 10.9 milligrams per ml, which is the dissolved and undissolved. CS is also given in the question. CV is given in the question. the R, the resistance, is also given in the question, and the diffusivity or diffusion coefficient is also given in the question. The effective concentration is being calculated, which equals A, the concentration dissolved or undissolved, minus half CS plus CV, and it is 9.72 milligrams per ml. Then the DR effect A star is also calculated, and it equals 0.7196 milligrams per centimeter square. This is simple calculation la DRA star. Then also the Q is being, the A star CST is also calculated, and then the Q is also calculated, and it equals 0.9 milligrams per centimeter square. Capsule type device. The silastic capsule has become a popular sustained release and controlled release delivery form. The molecules of the crystalline drug lying against the inside wall of the capsule leave their crystals. These are the molecules of the crystalline drug. They leave their crystals, pass into the polymer. This is the polymer, into the polymer wall by dissolution process. They diffuse through the wall and pass into the liquid diffusion layer. This is the liquid diffusion layer, and the medium surrounding the capsule. The concentration difference across the polymer of the wall, this is called HM, which is the concentration difference across the wall, and the stagnant diffusion layer thickness is called HA. This is the thickness of the aqueous diffusion layer, and they are represented by line CP minus CP, CM, and CS minus CB respectively, where CP is the solubility of the drug in the polymer, CM is the concentration at the polymer solution interface, that is the concentration of the drug in the polymer in contact with the solution. CS is the concentration of the drug in the solution at the polymer solution interface, and it becomes below the solubility of the drug at the interface. This is real difference in the solubility of the drug in the polymer and in the solution, although both exist at the interface. CB is the concentration of the drug in the bulk solution surrounding the capsule. One of the interesting things in the capsule type device, which will be shown in the next slides, is that we can obtain a zero order release using this technology. This is the drug release equation for a capsule type device, where Q is the amount of drug release per unit surface area of the capsule, and Kr is a partition coefficient. When diffusion through the capsule membrane is the rate limiting step or rate limiting factor, this is the equation that can be obtained. When the rate limiting step is diffusion through the aqueous diffusion layer, this equation can be obtained, and CS, as we mentioned, equals the partition coefficient multiplied by the CP, and in this case the amount released in case of aqueous diffusion layer control system equals diffusivity through the aqueous diffusion layer divided by the thickness of the aqueous diffusion layer multiplied by the CS multiplied by the time. The rate of drug release for a polymer control process can be calculated from the slope of a linear plot of Q versus time, and from the this equation, or the following equation. From this equation, the slope should be equal Cp multiplied by dm and divided by hm. This is when we have a membrane controlled process. For an aqueous diffusion layer, Q is divided by T for the diffusion layer control process results from a plot of Q versus time. The slope should equal CS multiplied by dA and divided by HA, the thickness of the aqueous diffusion layer. In an aqueous diffusion layer control system also, if we make a plot of Q versus amount released per time versus CS, the slope should be a linear relationship with the slope equals dA divided by the thickness of the aqueous diffusion layer. This is an example on the use or the application of a capsule-type device. Progesterone release rate, the partition coefficient Kr of progesterone is given in the question. The solution diffusivity, which is diffusion through the aqueous diffusion layer, is given. The silastic membrane diffusivity, which is dm, the diffusion coefficient through the membrane, is also given in the question. Solubility in the membrane is given in the question. The thickness of the membrane is given in the question. The thickness of the aqueous diffusion layer is given in the question. They ask you to calculate the rate of release of progesterone from the capsule as micrograms per centimeter square per day, and they ask you to compare it with the experimental result that was obtained from the slope of Q versus time, which was found to be 64.5 micrograms per centimeter square per day. The amount released per time is calculated using the equation for the capsule-type device, and it was shown to be, theoretically, it should be around 65.34 micrograms per centimeter square per day.